Okay, so I'm going to be going over some hints and answers for this homework for week 6, which corresponds to Lagrange's theorem and Cosets. So in the first problem, it is a visual problem concerning this diagram and some other diagrams and cosets. And part A is pretty straightforward, just getting a grounding on what elements are going to be contained in H, this cyclic subgroup. And so the elements in H are the ones that are just in the top row. And the diagram that corresponds to the coset big HG, well, the big HG diagram is going to highlight the elements that we get by going to H right away and then following the G arrow. So what are the G arrows? Well, the G arrow is the red arrow because that's the one that goes from the identity to the element 1, 0. Okay, so little g is the red arrow here. Okay, so which diagram shows this idea that we first are on the elements of our set and then we follow the red arrows? Well, we see that there's really only, it's only the second diagram that we even have the 3 red arrows acknowledged, and we only have the original elements of the set acknowledged as well. So it's going to be the second diagram here. So we go to the elements of each first, and then we follow the red arrows from each element in H, and we end up on HG. Then that leaves the first diagram to correspond to little gh, and we get that because we follow the identity, we start on the identity and then we follow the little g arrow. So that's telling us follow the little g arrow. And then we do all of the big H things. So the big H things, well, that's the subgroup generated by 0, 1. So we do the 0, 1 arrows until we get back to, or we do the 0, 1 generating arrow until we get back to our original. So in this case, the 0, 1 arrow is the blue arrow that's given to us. So we can just follow it. Okay, to the right and back again. And then in the last part, you want, these two things are equal because they are highlighting the same nodes. And then in the last part, you want to look at group explore to do something similar with kind of your own group. Okay, in this case, you're exploring some groups that you get from this diagram. And the key thing here is that you want to look at a product. And this product is a subset, but not a subgroup because it isn't closed. If you do a couple of the actions side by side, so you do an H action and then a K action, you will not get closure. You'll get, I think, the third flip that isn't in either one of these. And the condition of the product of subgroups theorem in 7.2 that it doesn't satisfy sorry, I was actually on the 7.2 theorem for 2 finite subgroups of a group, the set HK. Okay, so in my reading, it only actually shows that it defines a set, not a subgroup. Oh yes, this is one of the ones that I corrected in with some of the groups. Okay, so it satisfies all of the conditions. The theorem doesn't actually tell you when this is a subgroup. It only tells you that it is a subset. This is actually something that was like moved around, I think, between editions, and this is a holdover of my sheet. So you can kind of cross this off because it does actually satisfy all of these conditions. Okay, this theorem's incredibly versatile. Yeah, and it gives you another application. It doesn't actually tell you to do anything in Part C. Number 3 is a little bit playing around with the definitions. Number 4 asks you to prove that orbits of members of an S constitute a partition. So to know what a partition is, you should go back to chapter 0. And what you need to show is that every element of your set S belongs to some orbit, and that no two elements can belong to two different orbits. So the remaining exercises, the remaining 5 exercises, most of them have to do with applications of cosets and applications of Lagrange's theorem. And these are some of my favorite exercises. And if you do enough of them, these should become your favorite as well. They're always going to be a little bit challenging, but they should be within the realm of being able to be tackled. So I want to make sure that you do enough of these types of exercises where you get, suppose the order of the group is this, do some stuff, prove some stuff, do enough of these types of exercises so that they become your favorites as well. So if the order of the group is 155, then you want to show that the only subgroup of G that contains A and B is G itself. So I made sure to factor some of these ahead of time so I wouldn't be too embarrassed. And 155 has factors 1, 5, 31, and 155. Okay, so those are the prime factors. And so if A and B are non-identity elements, where they don't have the same order, then, well, the candidates, okay, so let's back up. So the order of A and B has to divide 155. So that's the reason why I wanted to know the factors of 155. So the orders have to be 1, 5, 31, or 155. Okay. If they can't be 1 because they're not identity elements. If the order is 155, then the group is G itself. Now let's think about the case where one of the elements is of order 5 and the other element has order 31. Well, in that case, I claim that the entire group has to be involved here. That if we have a subgroup of order 5 and we have a subgroup of order 31, we have to have the entire group. Now, if we want to use a theorem, we could use that theorem 7.2. But I think it's a lot easier to just think about it. Because the order of the intersection of the subgroup generated by A and the subgroup generated by B has to just be the identity. So if we throw A in and if we throw B in, then we have to get everything because they aren't going to overlap. And when we multiply them together, we're going to get an element that has order 155. Okay, in exercise number 6, we need to show that every proper subgroup of G is cyclic. So a proper subgroup of G has to have order P or it has to have order Q. So it has to be prime. And so if we have a prime order subgroup, well, then that has to be cyclic. Any prime order group is cyclic. In exercise 7, we want to find the intersection of a subgroup of order 12 and a subgroup of order 35. And again, it comes down to factors. So the factors of 12 are like 1, 2, 3, 4, 6, and 12. And the factors of 35 are 1, 5, 7, and 35. So they don't intersect at all. The factors of these orders don't intersect at all. So that means, so since the order of the intersection has to divide both H and K, that means that the order of the intersection has to just be 1. It has to just be the identity. Okay, and number 8, if G is an abelian group with an odd number of elements, show that the product of all the elements of G is the identity. The idea here is to match up the elements. So match up an element with its inverse. And what you need to do is show that an element cannot be the inverse of itself. And then you'll also just have the identity hanging out there, and the identity will be by itself. And then that's okay because your group as a whole has an odd number of elements. So the remainder should be able to be matched up. In question number 9, this is a real classic. You'll see it all the time. If you have a group with R subgroups of order P, and P is a prime number, you want to show that G has exactly R times P minus 1 elements of order P. The idea here is to take any 2 of those subgroups of order P, show that any 2 of those subgroups of order P must overlap in only the identity. And since they can only have the identity in common, and everything inside of one of those subgroups has to have order P, each one of those subgroups is bringing P minus 1 elements of order P to the table. Okay, so each one of these R subgroups is bringing P minus 1 elements of order P to the table. So that's where we get the R times P minus 1 elements of order P in total. In the final one, we have a group of order 25, and we want to either show that G is cyclic or that G to the power 5 is equal to the identity. So if G is cyclic, then we have an element of order 25, and we're done. If G is not cyclic, then what are the options? Well, the order of every element has to divide the order of the group. So the order of the group is 25. So the orders of the elements have to either be 1, 5, or 25. Well, we've eliminated the case where it's cyclic. So the other elements have to have order 1, or they have to have, not the other elements, sorry. So all the elements have to have order 1, or they have to have order 5. If they have order 5, this is true. If they have order 1, this statement here is also true. So that's it for order 25. And then the argument goes the exact same way if P is prime. Okay, so we reached the end of the assignment. I hope that these questions all make a little bit more sense now. We will be going over a little bit more about Cayley diagrams in class right before the mid-course test. Okay, hope this helps.